boundary layer that grows, that would be a laminar section and a turbulent section. Let me draw some arrows here. So once there's a transition to turbulent, it's going to stay turbulent. Now, there is a transition region that actually exists physically, but for the purposes of, in this class, for the purposes of calculation, the flow will either be laminar or turbulent, such that this position here is what we call the transition point. And that transition point would be labeled X sub CR. And that's just what we call a critical position, in that it is the position at which a transition from laminar to turbulent will be considered to occur, rather than there being a transition region here. So we use the definition of the Reynolds number, and here I'm going to put a subscript X to indicate that it's a function of X, is equal to the free stream velocity U infinity times the X position divided by the kinematic viscosity. And actually, I think in your textbook, they use, let's see, for free stream velocity, in many cases, they'll just use a V. So this can be written as U infinity or capital V as that velocity of the fluid away from the plate. So in either case, I mean, if you're using V, it just replace this U infinity that I've drawn here. This is the definition of the Reynolds number that could also be written as the density times the free stream velocity times X divided by the dynamic viscosity. Again, where nu is the kinematic viscosity and mu is the dynamic viscosity. This will give us an expression of the Reynolds number that is a function of X. So at X equals 0, the Reynolds number is 0. At X equals L, the Reynolds number is its maximum value, and anywhere between 0 and L, we can identify the Reynolds number. Well, for Reynolds numbers less than 500,000, 5 times 10 to the 5th, this is what's considered to be a laminar flow. For Reynolds numbers greater than 5 times 10 to the 5th, we consider it to be turbulent. So that we define a critical Reynolds number that is 5 times 10 to the 5th, and that would then be equal to the free stream velocity times X sub CR divided by the kinematic viscosity. So if you wanted to find, well, where is that position that we would consider the fluid to transition from a laminar flow condition to a turbulent flow condition, we'd say, okay, well, the critical Reynolds number is 5 times 10 to the 5th. So if I set that equal to the velocity times that critical position at which the transition will occur divided by the kinematic viscosity, it just says that X sub CR would just be the kinematic viscosity nu divided by U infinity times 5 times 10 to the 5th here. So anytime that you're given the fluid and the velocity of the fluid, you can determine what the position is at which laminar to turbulent transition would occur. And that's important because as I've started to present some of these correlations, there are correlations used to find the heat transfer coefficient when we're in the laminar section, and also when we're in the turbulent section or laminar or turbulent condition for the flow, such that the heat transfer coefficients are highly dependent on whether or not the flow is laminar or turbulent. Now, this green line that I've drawn is an indication of the velocity boundary layer, in that here, this expression of laminar or turbulent has to do with the hydrodynamic part of the problem, such that the velocity boundary layer, lowercase delta here, is a designation of the area in the flow where the no-slip condition has an effect such that all along the surface of this plate, the velocity of the molecules is zero. Outside the velocity boundary layer, the fluid everywhere out here is U infinity or V, whatever variable you're using for what's called the free stream velocity. Inside the boundary layer is where we have velocity gradients that actually exist in the fluid. In the laminar section, we can define the thickness of this boundary layer measured from y equals 0, which is on the surface of the plate, upward into the free stream, so that for the laminar condition, the boundary layer thickness delta is defined as 4.91 times the x position divided by the Reynolds number raised to the 1/2 power. So that this expression of the boundary layer thickness for the laminar flow condition from x equals 0 up to this transition point, this is how we could define that expression. Now we can also look at, well, at what rate does this boundary layer grow? Well, if I substitute in the definition for the Reynolds number, so this becomes 4.91 times x divided by the Reynolds number. Well, the Reynolds number is defined as the free stream velocity times x divided by nu, and this quantity is raised to the 1/2. So this expression then, if I take the x and consider that x is to the, this is like a minus 1/2 here since it's in the denominator, and here this is like an x to the first power. So this can be written as 4.91 divided by the free stream velocity divided by the kinematic viscosity to the 1/2 times x to the 1/2, where the free stream velocity and the kinematic viscosity of the fluid would just be constants. And so if as x increases, at x equals 0, the boundary layer thickness is 0. But as x increases, the boundary layer thickness increases with x to the 1/2 power. And so that would describe the thickness of the boundary layer all the way up until we get to this transition point that is x sub CR. Now, once we get to the turbulent flow condition, the boundary layer thickness grows at a different rate just due to the nature of the turbulent flow. In the laminar flow condition, essentially the molecules of fluid just slide past one another in layers. In the turbulent flow condition, we still have a laminar sublayer very close to the surface, but everywhere above that laminar sublayer, all the way up into the boundary layer thickness, we have rotation of the fluid. And what that does is it actually enhances heat transfer, but it increases pressure drop associated with the hydrodynamics of the problem. So the thickness of this boundary layer grows at a different rate inside once we get to a turbulent condition, which is from the transition point on down the rest of the plate. And this boundary layer thickness for the turbulent flow condition is 0.38 times x divided by the Reynolds number raised to the 1/5 power. So again, if I substitute in the expression for the Reynolds number, this expression becomes 0.38 times x divided by the free stream velocity times x over nu to the 1/5 power, which is like a minus 1/5, and here this is a 1. So this expression becomes 0.38 times the free stream velocity divided by the kinematic viscosity to the 1/5 power times x to the 4/5. So the rate at which the boundary layer thickness grows once we get to the turbulent flow condition is a higher rate of growth with x because it's raised to the 4/5 power rather than to the 1/2 power. So just by substituting in the expression for the Reynolds number, we can see the functional dependence of the boundary layer thickness, whether it's a laminar or a turbulent condition, and see what that exponent is that is actually on the x there. Now, when we consider This boundary layer thickness, again, this is just the hydrodynamics part of the problem. When it gets to the heat transfer part of the problem, this is a correlation that just defines the boundary layer thickness as a function of x, as the fluid flows parallel to the surface. For the heat transfer portion of the problem, correlations for the laminar and the turbulent flow conditions differ and are presented for these two flow conditions. Because of the way that the molecules of fluid that flow over the plate interact with the surface, it gives rise to different heat transfer coefficients, which are going to define the heat flux by convection, as there's a temperature difference that exists between the plate and the free stream, the fluid that's existing outside of the what will be the thermal boundary layer. And in that multiplied by that temperature difference is that heat transfer coefficient, so that we can write expressions for the heat flux in terms of the heat transfer coefficient and the temperature difference that occurs. So here the heat flux by convection is just H times Ts minus T infinity. So if the heat transfer coefficient changes as a function of position, and we consider, let's say, the surface temperature to be a constant and the free stream temperature to be a constant, then as H changes, so will the heat flux by convection. Now, the correlations that are presented for heat transfer are not expressed directly for as an expression of the heat transfer coefficient. The dimensionless parameter that is the Nusselt number is defined, and then we use the definition of the Nusselt number to calculate what the heat transfer coefficient is based on the conditions that are stated, or based on the conditions that exist in the problem. So for the laminar flow condition, the local Nusselt number, so this subscript x is an indication of a local value, just like the Reynolds number with the subscript x, that is the local Reynolds number. So the local Nusselt number in the laminar region is 0.332 times the Reynolds number raised to the 1/2 times the Prandtl number raised to the 1/3. And here, let me put the x position there. So the Reynolds number we'll use, which is that hydrodynamic expression of the dimensionless parameter. And recall that the Reynolds number is an expression of the ratio of the inertial forces to the viscous forces that act in the fluid. And when I presented the Prandtl number the last time, the Prandtl number is the kinematic viscosity divided by the thermal diffusivity. So it's an indication of how well the fluid dissipates momentum, or let's say diffuses momentum, compared to how well it diffuses thermal energy. So this is a dimensionless expression. So there are no units associated with any of these parameters. The Nusselt number, the Reynolds number, and the Prandtl number, all of those are dimensionless parameters. This expression of the Nusselt number is for flow over a flat plate that is isothermal, so that the temperature over the plate is a constant, and it's considered to be smooth in that the roughness of the surface doesn't have to be considered. Now, if we calculate the Reynolds number, which is based on the kinematic viscosity, kinematic viscosity of the fluid, the free stream velocity, and the x position, and the Prandtl number, which is just a ratio of the kinematic viscosity to the thermal diffusivity, I'm going to expand this expression with the definitions for each of these. So the Reynolds number is the free stream velocity times x divided by the kinematic viscosity to the 1/2, and the Prandtl number is the kinematic viscosity over the thermal diffusivity, alpha, raised to the 1/3 power. So here, this local Nusselt number for the laminar flow region Here we're going to have a free stream velocity that will be specified. The kinematic viscosity is a property of the fluid that we can look up at what is called the film temperature, and I'll define that in a second. And the thermal diffusivity. The thermal diffusivity is another property that is just the thermal conductivity divided by the product of the density and the specific heat. But here, all of these would be constants except for X. So the Nusselt number here would vary with X to the 1/2. Now, the Nusselt number is not enough yet. That's just, again, a dimensionless parameter. The Nusselt number, the local Nusselt number, Nu sub X, is defined as the local heat transfer coefficient times the X position divided by the thermal conductivity of the fluid. So using the definition of the Nusselt number, which from the last time I just wrote as the heat transfer coefficient times a characteristic length divided by the thermal conductivity of the fluid. Here, this expression allows me to then determine what the local heat transfer coefficient is from a correlation that defines the local Nusselt number correlation. So, or a correlation that defines a local Nusselt number. So if I rearrange this expression for H as a H sub X, it says that H sub X would be equal to the thermal conductivity divided by X times 0.332 free stream velocity times X over nu to the 1/2 nu over alpha to the 1/3 power. So again, these fluid properties would all be constants. The free stream velocity would be a constant. The thermal conductivity would be a constant. All of the things that we would either be given in a problem or we look up from the tables. And so all we have is the functionality of X. So here we have an X to the 1/2 and an X to the -1. So this expression can actually be written as K times 0.332 times U infinity over nu to the 1/2, nu over alpha to the 1/3, X to the -1/2, because here again we have X to the 1/2 and an X to the -1. So this expression says that the local heat transfer coefficient, H subscript X, is equal to all these constants times X to the -1/2. So this says that the heat transfer coefficient H decreases in the laminar region of flow over the plate with a functionality that is X to the -1/2. And notice that the heat transfer coefficient is considered to be infinite at the leading edge of the plate. When X is equal to 0, this value goes to infinity. So at this very leading edge, which is at X equals 0, we would consider that the heat transfer coefficient is an infinite value, but it decreases very quickly as we start to substitute in positions in X that are greater than 0. So we could draw an expression of the heat transfer coefficient. Let's see, I'll put it here. H as a function of X. So here I'm going to just label the transition point so that everywhere to the left of that transition point is laminar, and everywhere to the right would be turbulent. So from X equals 0, we'll look something like this, in that here X, H varies with X to the -1/2 here, such that it's infinite at X equals 0, and it decreases with X to the -1/2 all the way till we get to this transition point. Now, when we consider the turbulent flow condition, again, because of the differences in the way that the fluid actually interacts with the solid surface, where we have heat transfer occurring, in the turbulent flow condition, we have the definition of a Nusselt number a local Nusselt number, NU sub x, and it is 0.0296 times the Reynolds number raised to the 4/5 times the Prandtl number raised to the 1/3 power. So a slightly different expression. And for most external flow correlations, you're going to see an expression of a constant times the Reynolds number raised to a power times the Prandtl number raised to a power. That's because in the definition of a heat transfer coefficient, which is a function of fluid properties and geometry and the way that the fluid moves over that surface, well, the Reynolds number embodies the hydrodynamic contribution to the heat transfer coefficient. The Prandtl number embodies the combination of the hydrodynamic and the thermal problem in the definition of that Prandtl number. So we get an expression for the Nusselt number that is a function of the hydrodynamics and the thermal conditions that exist in the problem. If I make substitution for the Reynolds number and the Prandtl number here, this expression becomes 0.0296 times the free stream velocity times x over the kinematic viscosity to the 4/5 power times the Prandtl number, which is the kinematic viscosity over the thermal diffusivity, lowercase alpha here, to the 1/3 power. And if we set this equal to the definition of the Nusselt number, the local Nusselt number, this is H sub x times x over the thermal conductivity of the fluid. So that here, the heat transfer coefficient, H is a function of x, can be written as 0.0296 U infinity over, well, actually, let me start over here at the top here. The heat transfer coefficient will be K over X times 0.0296 times the free stream velocity times X over nu to the 4/5 nu over alpha to the 1/3. So that if I, again, consider what the constants are, the thermal conductivity, the kinematic viscosity, the thermal diffusivity, the free stream velocity. So here I have x to the 4/5 and x to the -1. So this expression can be written as k times 0.0296 times the free stream velocity over the kinematic viscosity to the 4/5, the kinematic viscosity over alpha to the 1/3 times x raised to the -1/5. Now this just says that the heat transfer coefficient will decrease with x, just like it does in the laminar flow condition, but it just decreases at a lower rate, x to the -1/5 rather than to the -1/2. So here, due to that transition region that physically exists being reduced to a transition point, here we would actually have a different starting point at the same position. Let me just extend it on. Let me move some of these things here. H varies with x to the -1/2. Like here, this is just an indication that H varies with x to the -1/5 here. So the rate of change is slower for the heat transfer coefficient once we get into the turbulent flow condition. Now, for these expressions, what these two expressions do for us, this Nusselt number correlation and this one, they both allow us to find the heat transfer coefficient at any point along the length of that plate. So if I need to find the local heat flux, the heat flux by convection at any point along the length of my plate, that means I need to know, well, what is the temperature difference, such that for an isothermal surface everywhere along the entire length of the plate, the surface temperature will be known. The free stream temperature is a constant also. So I just need to find the heat transfer coefficient at a particular point. whether it's in the laminar or the turbulent flow condition. And when I calculate that heat transfer coefficient, if it's in the laminar region or if it's in the turbulent region, I can calculate exactly what the heat flux is at that particular position. Now, if I wanted to find average values of the heat transfer coefficient, then I would have to consider integrating over a length of the plate in order to find an average value. So if I'm looking here at the laminar flow condition, or the laminar region, which is from x equals 0 to the critical point, the heat transfer coefficient varies from an infinite value at x equals 0 down to its minimal value at the transition point. So there's an average that would exist from the leading edge to a transition point, or from just the leading edge to any position that is still in the laminar region. And that expression can be written for the laminar region as, with a different color here for, actually I'll write this, laminar, and I'll just write a difference in the expression. When you see the Nusselt number without a subscript, that's an indication that it's an average Nusselt number. And the correlation that would be used in order to find that average Nusselt number is 0.664 times the Reynolds number raised to the 1/2 Prandtl number to the 1/3. So that this would be equal to the average heat transfer coefficient times the x position divided by the thermal conductivity. Now, when using this expression, this is going to give you the average heat transfer coefficient from x equals 0 to whatever position, as long as that position is less than or equal to the transition point. So this is another reason that you want to be able to find the transition point, so you can determine, well, what is the extent or what is the length of the laminar region of flow over the plate. The flow will always start out as laminar and have to transition from laminar to turbulent. The only time that you're going to see turbulent flow over the entire plate is if there's an indication of a tripwire, which basically induces a rotation into the fluid before the fluid starts to move over the plate. Otherwise, the transition has to occur from laminar to turbulent. But this expression here will give us the average heat transfer coefficient that exists from the leading edge of the plate to any position that is still in the laminar region of the plate. For the turbulent flow condition, the average Nusselt number is 0.037 times the Reynolds number to x to the 1/2 times Prandtl to the 1/3. And so this will be the average heat transfer coefficient times x divided by the thermal conductivity. Now this expression for the turbulent flow condition, because the turbulent flow condition does not begin at the leading edge, there's a laminar flow condition. Now, depending on what the flow conditions are, the laminar region can be really long or it can be really short, but this expression is only valid for the condition where it's actually a turbulent flow. So this expression would not be applicable to a problem such that we would be integrating from the leading edge, because the leading edge is the beginning of the laminar flow region. We'd have to find the transition point, x sub CR, and integrate, or this would be the expression for the average heat transfer coefficient for what would just be the turbulent region of the plate. So if I want this average value, that's going to be from this critical point to some other position in x along the length of the plate there. Is it not RE to the point? Oh, yeah, I did. I wrote that incorrectly. This should not be 1/2. This should be the 4/5 here. I think I said 4/5, but wrote 1/2 there. There's a different functional dependence. So this expression for the turbulent will only give you the average for just the turbulent region. Now, depending on the case for the flow, and we look back here at this transition point is based on the Reynolds number. The Reynolds number is defined as the free stream velocity times x over the kinematic viscosity. And the critical Reynolds number is 5 times 10 to the 5th. The higher the velocity, the higher that the calculated Reynolds number will be. The lower the kinematic viscosity, the higher that Reynolds number will be. Well, I can certainly, depending on the fluid that's selected and the velocity, along with the length of the plate or the length in the flow direction that I'm measuring, I could have a condition where the length of the plate, when I substitute in the length from the leading edge to the trailing edge of the plate, which would just be the length of the plate, if I calculate that the Reynolds number at the end of the plate, the trailing edge of the plate, so here, at the trailing edge of the plate, if I find that the Reynolds number is less than 500,000, then I know that there's laminar flow over the entire length of the plate. If I calculate the Reynolds number at the trailing edge of the plate, and I find it is greater than 500,000, that means I have a laminar region and a turbulent region. When I have a laminar region and a turbulent region, the expression for the heat transfer coefficient over the entire plate would have to take into account that I have a laminar region and a turbulent region. When we have that condition for laminar plus turbulent, when we're trying to find an average heat transfer coefficient, the Nusselt number is defined as 0.037 times the Reynolds number raised to the 4/5 minus 871, this entire quantity multiplied by the Prandtl number to the 1/3. This will give us the average heat transfer coefficient times x over the thermal conductivity. This expression we use when we have a laminar and a turbulent flow condition that exists over the entire length of the plate, and we want to get the average heat transfer coefficient that exists over the entire length of the plate. The first expression that I gave you for the laminar flow condition, the average Nusselt number, which allows you to get the average heat transfer coefficient, is going to allow me to calculate the average heat transfer coefficient just in the laminar region. For the turbulent, just in the turbulent region. So we'll use these expressions to find heat transfer coefficients depending on the question that's being asked. If someone asks me, well, for a plate where I have a laminar region and a turbulent region, what is the average, what is the heat flux, the average heat flux out of just the section that's covered by the laminar flow? Well, that will say I have to find the average heat transfer coefficient just for the laminar region, multiplied by Ts minus T infinity, and that would give me the average heat flux in the laminar region. Then since I would have found the transition point, from the transition point to the trailing edge of the plate, I would find the average value of the heat transfer coefficient using the turbulent correlation to get that heat transfer coefficient and multiply by the same Ts minus T infinity, and that will give me the heat flux just out of the turbulent region. If I wanted the average heat flux over the entire plate, the average heat flux for the entire plate is the average heat transfer coefficient over the entire plate multiplied by Ts minus T infinity. And I would use this expression, laminar plus the one for laminar plus turbulent, so that I would consider, I'm considering that over the entire length, I have a laminar section and a turbulent section. So whenever we're writing expressions for heat transfer coefficients, we have to consider, well, what is this heat transfer coefficient actually being used for in order to determine what the which correlation should be used to get that actual heat transfer coefficient. So we'll look here at a couple of problems, and all of these properties that are used for the laminar and turbulent flow conditions, whether we're calculating an average Nusselt number or a local Nusselt number to get an average heat transfer coefficient or a local one, we're going to evaluate the properties at what is called the film temperature. And the film temperature is written as T sub F, and it's just the surface temperature plus the free stream temperature divided by 2. Very simple calculation. And physically, it is the average temperature that exists inside the thermal boundary layer that will grow over this surface whenever there's a temperature difference between the fluid and that solid surface. So recall that if I have a plate that has a temperature Ts and there is a free stream temperature T infinity, when that boundary layer grows over the surface, the temperature outside the boundary layer is everywhere T infinity. The temperature on this surface is considered a constant for an it is constant for an isothermal plate. So inside this boundary layer is where we have temperatures that vary between T infinity and Ts. And so since all the heat transfer actually occurs inside this boundary layer, the film, this is called a film temperature, this thermal boundary layer is viewed as a film because it's very thin, and it will be defined, the film temperature will be defined as just the average temperature between the fluid and the solid surface, because all the fluid inside of that thermal boundary layer is somewhere between Ts and T infinity. So we would use that film temperature to evaluate in the Reynolds number what would be the kinematic viscosity, and in the Prandtl number, the kinematic viscosity and the thermal diffusivity. Now, depending on what fluid you're looking at, many cases, the Prandtl number is already calculated for you, because the Prandtl number is just a ratio of the two quantities that are the kinematic viscosity and the thermal diffusivity. Ricardo, no, I'm not going to go over the non-dimensionalized equation from chapter 6. Those are what are used to develop the expressions that are presented in chapter 7. So these properties are evaluated at this film temperature so that we can get the properties that exist for the fluid where all of the heat transfer is occurring in. And the reason I'm saying all the heat transfer occurs inside the thermal boundary layer is because recall that heat transfer occurs when there's a temperature difference. Once we get outside the thermal boundary layer, the fluid temperature is everywhere T infinity, the free stream temperature. So there's no more heat transfer actually occurring out here in the free stream, where the temperature is a constant. It's all occurring inside the thermal boundary layer where there are different temperatures that actually exist, so that heat transfer is facilitated from the plate eventually out into the fluid. It's just that once it's out here in the fluid where the temperature is uniform, there's just no more heat transfer that's actually occurring. So we'll look at, well, how do we go about using these expressions to then calculate convection heat transfer rates? So here's an example here. I'm going to go reference a few examples with different fluids. And so here we'll consider flow over a flat plate. And here the fluid is engine oil. So we have a plate here that is of length L with a fluid moving with a given velocity and free stream temperature. So that the plate is going to have a definite have dimensions associated with it and a surface temperature, so that we can determine some quantities based on the correlations that I just presented here. So here we'll consider that the free stream temperature for the engine oil is 150 degrees C. The surface temperature on the plate is 50 degrees C. The free stream velocity of the fluid is 2 meters per second. And the length of this plate is 2 meters. We want to determine, well, what are the heat fluxes? What is the heat flux at x equals L? X equals L over 2. And I think that's going to give me, and these, when we say the heat flux at a position, that is a local heat flux. And here we'll consider what is the average heat flux. Now, the average heat flux is the heat flux that exists over the entire length of the plate, whereas the heat flux at a position is just what we call a local heat flux. So here at x equals L, this would be, well, what is the heat flux at this trailing edge? And what is the heat flux at L over 2? So just at the midpoint as we move from x equals 0 to x equals L, and the average heat flux, and actually I'll make this very specific, over the plate here. Now we know that by Newton's law of cooling, the heat flux is just the heat transfer coefficient times Ts minus T infinity. So if I want the heat flux at a position, that means I have to find the heat transfer coefficient at that position where I want to define the heat flux. If I want the average heat flux over the plate, then that means I need to find the average heat transfer coefficient over the entire plate. So with this being flow over a flat plate, we'll reference the correlations that I just presented and choose them appropriately based on the conditions that exist in the problem. Now here, to determine the heat transfer coefficient at x equals L over 2 and at x equals L, we have to consider, is the flow laminar or turbulent at x equals L over 2? Is the flow laminar or turbulent at x equals L? If it is laminar, if there's a laminar and turbulent region over the length of this plate, then this expression for the average heat transfer the average heat flux is going to be based on an average heat transfer coefficient that has to take into account that there's a laminar and turbulent region. If there isn't a turbulent region, then the average heat flux over the entire length of the plate would just be the average heat transfer coefficient for just a laminar flow for the entire length of the plate here. So how do we determine that? Well, that's going to be determined based on the Reynolds number. The Reynolds number, and if we calculate it at x equals L, this becomes U infinity times L over the kinematic viscosity for the fluid. If I find that at the trailing edge of the plate that it's laminar, then it's laminar over the entire length of the plate. If I find that it's turbulent at the trailing edge, that means that there's a transition point that exists over the plate, and I'd want to find exactly where it is, because if I have to calculate a heat flux at x equals L/2, I want to determine whether or not that is in the laminar region or the turbulent region. So we're going to start with determining, well, what is the Reynolds number at the trailing edge of this plate? But in order to do, we have the free stream velocity U infinity of 2 meters per second, but we need the kinematic viscosity. Well, the properties are all evaluated at the film temperature, which is just Ts plus T infinity divided by 2. So here the surface temperature is 50 degrees. The fluid temperature is 150 degrees. So we would just evaluate the film temperature, or use the film temperature of 100 degrees to evaluate the fluid properties that we'll use for all the calculations for this flow over this flat plate here. Now, in order to get the properties that we need, we'll have to reference the appendix of the textbook. And here, let's see here. In the appendix, in table A13, are the properties of multiple different liquids, but we also have, I don't recall, for water, which is going to be used quite a bit there, saturated propane, saturated ammonia, R134A. Yeah, water. For water is table A9. But here we're looking up for for engine oil. So I'll go back to A13 here. So we have methane, methanol, isobutane, a bunch of different fluids, but here we have the engine oil here. And at 100 degrees C, we have all these properties. So if I go back to the header, we have the density, specific heat, thermal conductivity, thermal diffusivity, dynamic viscosity, kinematic viscosity, the Prandtl number, and the expansion coefficient. So here, we're going to specifically be looking for the kinematic viscosity for the calculation of the Reynolds number, but recall that when we get to the Nusselt number, not only will we need the kinematic viscosity, but we'll also need the thermal diffusivity, but the ratio of the kinematic viscosity to the thermal diffusivity is the Prandtl number. So we'll just look that up directly. We'll also need the thermal conductivity of the fluid for the calculation of the Nusselt number to get to, or actually we'll need the thermal conductivity along with the Nusselt number in order to get to the heat transfer coefficient. So we'll go ahead and get all these properties. Again, here, the thermal conductivity, the kinematic viscosity, and the Prandtl number. So here, see, that's that column, and that one. And here, the Prandtl number and the kinematic viscosity. Oops, wrong line. So at 100 degrees, Prandtl and yeah. So we have these quantities from the table that allow us to move on with the calculations that we'll need. So the thermal conductivity of 0.1367. So K equals 0.1367 watts per meter Kelvin. The kinematic viscosity, 2.046 times 10 to the minus 5. And that the units here are square meters per second. And the Prandtl number, which is just the ratio of the kinematic viscosity to the thermal diffusivity, is 279.1. That's a dimensionless quantity. So now we have these properties that we need for the calculations of the quantities that we need in order to determine first what is the condition of the flow. So the Reynolds number, we calculate the Reynolds number at the trailing edge. So here the free stream velocity is 2 meters per second. I'll put the units in the first time just to show that they cancel. Times the length of the plate, which is 2 meters, divided by the kinematic viscosity of 2.046 times 10 to the minus 5 meters squared per second. So you can see here that in the numerator I have meters squared per second, and in the denominator the same. So here for right, 0.46. All right, so I get here that the Reynolds number is 195,503. That is less than 500,000. So it says that it's laminar flow at the trailing edge. So if it's laminar flow at the trailing edge, it's laminar flow over the entire length of the plate there. So with that being the case, then the expression for the expressions that we'll reference are all just going to be laminar flow expressions, so that when we calculate the heat flux at L/2 and at L, we just need the local values of the heat transfer coefficients in the laminar region for both of those positions, which allows us to then find the heat flux at those two positions. And then the average value of the heat flux is going to be determined based on the average heat transfer coefficient. So here at X equals L, since we already have the Reynolds number at X equals L, our expression for the local value of the Nusselt number just comes from this expression here. So here the Nusselt number is equal to 0.332 times the Reynolds number raised to the 1/2 times the Prandtl number to the 1/3. So here this is 0.332, and I just calculated the Reynolds number. So this is 195,503 to the 1/2 times the Prandtl number of 279.1 to the 1/3. So we can get the Nusselt number first. All right, try this into correct. All right, so the Nusselt number is 959.331. So that's just a dimensionless parameter. That's the Nusselt number. And actually, I want to, since I substituted in, I'll write this Nusselt sub L here instead of Nusselt sub X, because I'm putting in the Reynolds number evaluated at the position that was X equals L. So this is the Nusselt number at X equals L. This is equal to the heat transfer coefficient at X equals L times L divided by K. So this says then that the heat transfer coefficient at the trailing edge of the plate is equal to K over L times the Nusselt number at L. So here the thermal conductivity that we looked up was 0.1367 watts per meter Kelvin. The length of the plate is 2 meters, and the Nusselt number is 959.331. And so from this expression, we can get the heat transfer coefficient at the trailing edge. So times 0.1367 divided by 2 here. And so the heat transfer coefficient at the trailing edge of the plate is 65.57 watts per meter squared Kelvin. So using that heat transfer coefficient at this position that is the trailing edge of the plate, then the heat flux, here I'll write at L, is just the heat transfer coefficient at X equals L times Ts minus T infinity. So here this is 65.57 watts per meter squared Kelvin times the temperature difference. The surface temperature is 50 degrees and the fluid temperature is 150 degrees. So here we're going to end up with a negative value, and the negative value just indicates that the heat flux is into the plate. The fluid is actually heating the plate rather than the plate heating the fluid. So times minus 100 here. So minus 6,557.03 watts per square meter. Now here the degree C cancels with the Kelvin because this is a temperature difference. The temperature difference in degree C is exactly the same as the temperature difference in Kelvin. So those temperature units directly cancel. So this is the heat flux at X equals L, and it's into the plate again because the temperature of the fluid is greater than the temperature of the surface. Now here at X equals L over 2, the Nusselt number at L over 2 is 0.332 times, now this will be the Reynolds number at that position. So here I'm just going to substitute in the values here of 2 meters per second times 1 meter, just so this is clear what quantities we're actually using here. Because at L, if L is 2 meters, L over 2 is just 1 meter. We use the same kinematic viscosity. And this quantity will be raised to the 1/2 power times the Prandtl number of 279.1 raised to the 1/3. So here, this expression of the Nusselt number is determined based on a Reynolds number that changes because we're evaluating it at L over 2, or at the midpoint along the length of the plate. Let's see here. So let me go back to this recall here. There we go. So here, with the Reynolds number being just half of 195,503, it's raised to the same 1/2 power multiplied by 279.1 to the 1/3. Here, this Nusselt number at L over 2 is 678.35. So we have a difference in those quantities here. The Nusselt number at the trailing edge was 959.331, and here is 678.35. And it's a lower value because, of course, the Reynolds number is lower. This can be set equal to the heat transfer coefficient at L over 2 times the position that is L over 2 divided by the thermal conductivity. So the heat transfer coefficient at L over 2 is just K times the Nusselt number. Well, I'll write it this way. K, the thermal conductivity, divided by L over 2 times the Nusselt number at L over 2. So just rearranging the expression, and now we can substitute in the quantities here. The thermal conductivity is the same at 0.1367 watts per meter Kelvin. L over 2 is just 1 meter times 678.35. And so from here, we can get the heat transfer coefficient at L over 2. So times 0.1367. And this is 92.73 watts per meter squared Kelvin. So notice here that the heat transfer coefficient at L over 2 is higher than the heat transfer coefficient at L, and that's because recall that the heat transfer coefficient decreases with X, with the functional dependence that is X to the minus 1/2. So the closer I get to the leading edge of the plate, as I move closer to the leading edge of the plate, the heat transfer coefficient will get higher, so that at X equals 0, it will be considered an infinite value. So here, the heat flux at L over 2 then is just the heat transfer coefficient at L over 2 times Ts minus T infinity. So this is 92.73 watts per meter squared Kelvin times 50 minus 150. So that this heat transfer coefficient is minus 9,273.04 watts per meter squared. So those are local values of the heat transfer coefficient that are used to calculate local values of the heat fluxes at those same two positions. Now, those just tell us what the heat fluxes are. So if I wanted to indicate here, the heat flux is higher into the plate at this position, at L over 2, compared to the heat flux at X equals L. So here's the heat flux at L over 2, and this is the heat flux at L. With this, a line drawn for a heat flux near the leading edge of the plate would be much longer, as there's a decrease in the heat transfer coefficient from the leading edge towards the trailing edge, that is to the x to the minus 1/2, which was the reason I went to this point here. For the laminar flow condition, H is a function of X, varies with X to the minus 1/2. In the turbulent region, H is a function of X. The local values of the heat transfer coefficient vary with X to the minus 1/5 there. So here we have the two values for the local heat transfer coefficients to give us the local heat fluxes at the positions that are indicated at X equals L and L over 2. But now we want to get the average heat transfer coefficient. Let's see, the average over the plate. So if we know that the heat transfer coefficient varies with X to the minus 1/2, with it being infinite at X equals 0 and minimal at the trailing edge, because that's where the end of the plate is, the average heat transfer coefficient should be greater than 65.57, with the highest value being infinite at X equals 0. So this average value that we calculate, I mean, a good place, since it's a laminar flow condition over the entire length of the plate and it's always decreasing, that means that the average value should be greater than the local value at the trailing edge of the plate. And we'll consider something else when we look at this expression once we made the calculation. So if we want the average over the plate, and it's all laminar, then that says we can go back to the expressions that we had before. For the laminar flow condition, the Nusselt number is equal to 0.664 Reynolds to the 1/2, Prandtl to the 1/3, to get an average Nusselt number that will give us an average heat transfer coefficient. So here, the Nusselt number is equal to 0.664 times the Reynolds number to the 1/2 times the Prandtl number to the 1/3. Now here, the average is going to be from X equals 0. This correlation is developed based on starting at X equals 0 and moving out to some position that is still in the laminar region. So here, this Reynolds number at this X position is the X position at which our laminar flow region ends, where our laminar flow region ends at the end of the plate. So here, this Reynolds number is the same Reynolds number that was used to calculate the local Nusselt number at the trailing edge of the plate, because we're trying to get the average heat transfer coefficient over the entire length that goes from x equals 0 to x equals L, which is that trailing edge. So here, this expression becomes 0.664 times that Reynolds number of 195,503 raised to the 1/2 times the Prandtl number. The Prandtl number that was 279.1, and that's raised to the 1/3. So here, the only thing that's different is that coefficient that is out front, and it's just double the value that is the value that we calculated for the or that appears in the local Nusselt number correlation. So here, let's make this substitution here. So the Nusselt number, that is the average Nusselt number, is 1,918.66. Again, that's a dimensionless quantity. And so with that Nusselt number defined, then this is equal to the average heat transfer coefficient times, here, this is going to be at x equals L divided by the thermal conductivity. So here this says again that the average heat transfer coefficient would be K over L times that Nusselt number. So here the thermal conductivity is still 0.1367. Yeah, 0.1367 watts per meter Kelvin. At that position, that's the end of the plate, is 2 meters times this average Nusselt number, 1,918.66. So here, then the average heat transfer coefficient is 131.141 watts per meter squared Kelvin as the average heat transfer coefficient, so that the average heat flux then is 131.141 times 50 minus 150. So this is minus 100 or 13,114.1 watts per square meter. Now we look here at the average heat transfer coefficient over the entire length of the plate and compare that to the heat transfer coefficient at the trailing edge of the plate. This expression of the average heat transfer coefficient is exactly twice the value of the value that is at the end or the trailing edge of the plate. Anytime that you have a laminar flow condition over the entire length of the plate, the average heat transfer coefficient over the entire length is just going to be equal to double the value of the heat transfer coefficient at the trailing edge. So here, where the heat transfer coefficient was 65.57 at the trailing edge, the average heat transfer coefficient was 131.14. That's just by the nature of the exponent that's on X. The local Nusselt number correlation is 0.332, Reynolds to the 1/2, Prandtl to the 1/3, but that heat transfer coefficient variation for the laminar flow region is x to the minus 1/2. Another, if you wanted to more directly calculate the average heat transfer coefficient, I could consider integrating h as a function of x, this entire expression, from 0 to x through if I integrate h as a function of x, the average heat transfer coefficient is just the integral from 0 to L of hx dx times 1 over L. H is a function of x. Here's this local heat transfer coefficient. Here, this is the average heat transfer. This is how you get the average heat transfer coefficient. If I put this expression in the integral, the only thing that changes the function of x is x to the minus 1/2. And we'd end up with a value that is twice the value that is the heat transfer coefficient evaluated just at x equals L. And thus, the expressions of the local Nusselt number for the laminar region, which is 0.332, Reynolds to the 1/2, Prandtl to the 1/3, the average value, here it is, it's right there. The average value for the Nusselt number in the laminar region is 0.664. It's just twice the value. So if I evaluate the local Nusselt number at the trailing edge, it'll just be half the value of the average, or vice versa. The average value will be twice the value that is evaluated at the trailing edge. But that only applies to the laminar region, and that's just because x varies to the minus 1/2. And so when you integrate through the expression, you'll get a value that for the average value that's twice the value that you calculate at the trailing edge. That's not true for the turbulent region, because in the turbulent region, x varies to the minus 1/5. So you have a different functional dependence that is integrated to get to an answer for that quantity. So that only applies to the laminar flow region with regard to the average value being twice the value at the trailing edge. Now let's look at a different flow over a flat plate problem where we're looking for looking for other quantities. So here, let's consider the same configuration in that there is a plate. Say flow over a flat plate. And here we'll consider that air is moving over the plate rather than engine oil, so we can look up some other properties. And so we'll consider air flowing over this plate that is of length L. And the air is moving, again, with a free stream velocity and free stream temperature. And we'll consider the isothermal condition for the surface of this plate. Now here, the air has a temperature T infinity that is 20 degrees C. And the surface temperature is 180 degrees C. The fluid velocity, U infinity, is 50 meters per second. And here the plate is 1/2 meter long. For this problem, we want to determine, well, let's find the average heat transfer coefficient over the plate. And also, well, actually, let's say the heat flux, the average heat flux over the plate. And let's look at how the average heat flux over the entire plate compares to the average heat flux in the laminar region and the average, just in the laminar region, that'll be fine. So here, different fluid, different conditions specified for the problem, but it's still a flow over flat plate problem. So if we're going to determine the expressions of the heat flux over the plate and the heat flux in the laminar region, we have to make sure that we are calculating the appropriate values. The heat flux in the laminar region and the heat flux over the entire plate were exactly the same for the previous problem because it was laminar flow over the entire length of the plate. Here, I'm implying that there's going to be a laminar and a turbulent region because I'm asking for two different two heat fluxes. One is the heat flux over the plate, and one is over the laminar region. Now, if you found that it was laminar flow at the trailing edge, those would be exactly the same quantities. The only way that we would have a heat flux, an average heat flux in the laminar region that would be different than the average heat flux over the entire plate is that there was a turbulent section associated also with this plate. So the first thing you want to do is to find out, well, where's the laminar and where's a turbulent region, if a turbulent region even exists. So here, that means we find the Reynolds number, evaluate it at the trailing edge of the plate, because if it's laminar there, it's laminar everywhere. If it's turbulent, then there's a transition point. So here, the Reynolds number will be U infinity times L over the kinematic viscosity. Now, all of these properties will be evaluated at the film temperature, which is the surface temperature plus the free stream temperature over 2. So here, the surface temperature is 180 plus 20 over 2. So here, 100 degrees C again, but this is for air. So for air, and in particular, we're going to consider this is air at atmospheric pressure. Because there is a table in the same appendix that has it for at different elevations, so that the pressure is less than what we consider to be atmospheric pressure. But for and I'll refer to this particular one when we turn to it. But we would want to get the same properties, because in order to find the Reynolds number, we need the kinematic viscosity. And the Nusselt number correlations are going to be dependent on that Reynolds number that we calculate using the kinematic viscosity. To get that Nusselt number, we'll need the Prandtl number. And to go from a Nusselt number to a heat transfer coefficient, we'll need the thermal conductivity. So we'll still want to get all of those properties, the kinematic viscosity, the Prandtl number, and the thermal conductivity for air evaluated at the film temperature that is 100 degrees C. So I'll go back to the appendix here. And for atmospheric air, that is table A15. So here we have properties of air at 1 atmosphere. And here we're evaluating at 100 degrees C for the film temperature. So here the thermal conductivity, the kinematic viscosity, and the Prandtl number. Now, particularly here, notice the large difference in the Prandtl number. The Prandtl number is 0.7111 compared to, I think it was 279.1. Remember, the Prandtl number is defined as the kinematic viscosity over the thermal diffusivity. For numbers much greater than 1, or typically greater than 1, we consider that it's a much better diffuser of momentum compared to thermal energy. For Prandtl numbers less than, well, actually, I think it's about 0.1. I don't recall, but this expression is of the Prandtl number is a ratio. So really high numbers, it just says it's going to diffuse momentum better than it does heat or thermal energy. And for lower values, it says that fluid comparatively will dissipate thermal energy much better than it does momentum. So here are the quantities then that we would have to reference in order to calculate the Reynolds number, the Nusselt number, and eventually the heat transfer coefficient. So here are thermal conductivities, or the thermal conductivity, kinematic viscosity, and Prandtl number. So for the thermal conductivity, this was 0.03095. For the Prandtl number, 0.7111. And for the kinematic viscosity, 2.306. times 10 to the minus 5 meters squared per second. So we have these quantities, and this was table A15. So we have the quantities that we need to make the calculations. Again, we want to find out at the trailing edge, is it turbulent or is it laminar? So we can select the appropriate correlations to eventually get an average heat transfer coefficient over the plate. So here the Reynolds number will be the free stream velocity of 50 meters per second times the length of the plate, which is 0.5 meters, divided by the kinematic viscosity of 2.306 times 10 to the minus 5. All right, and here I get a value that is 1 million, over 1 million, so 1.08413 times 10 to the 6. Now that's greater than 5 times 10 to the 5th. So it says that this is a turbulent flow condition at the trailing edge of the plate. So what that means is that there's a laminar region and there is a turbulent region that exists. And we want to find out, well, how long is the laminar region and how long is the turbulent region? So here, X sub C, well, actually, I'll write this first. The critical Reynolds number is 5 times 10 to the 5th, which would be U infinity times the critical position or the transition point divided by the kinematic viscosity. So this says I can calculate this quantity as the kinematic viscosity over the velocity times 5 times 10 to the 5th. So that kinematic viscosity was 2.306 times 10 to the minus 5. The free stream velocity is 50 meters per second times 5 times 10 to the 5th. All right, and so it says here that the transition point is at 0.2306 meters. So if the length of the plate is 1/2 a meter, and this is just short of the halfway point is where the laminar region. So this just says the laminar region is from 0 to 0.2306 meters. And the turbulent region is from 0.2306 to 0.5 meters. So that's how we could determine, well, what are the proportions of laminar to turbulent, laminar and the laminar region and the turbulent region. Now here, the only reason we really need to know this is because I've asked for the average heat flux in the laminar region, because the average heat flux over the entire plate is just going to be based on the existence of a laminar and turbulent. It doesn't matter whether the the laminar region was, if it was 0.1 meters and 0.4 was turbulent, or if the laminar region was 0.4 meters and the turbulent was 0.1 meters. The expression of the correlation that is for the combination of a laminar and turbulent region takes into account that there's a distribution, and that distribution is taken into account through the definition of that Reynolds number, and also through that X position that will be used to take the Nusselt number to a heat transfer coefficient. So this expression for the heat flux average over the plate, this expression then is H average over that entire plate times Ts minus T infinity. And over the entire plate, I have a laminar region and a turbulent region. So the expression that would be appropriate for the determination of that average Nusselt number when I have both is going to be based on the expression that says the Nusselt number is 0.037 times the Reynolds number raised to the 4/5 minus 871 times the Prandtl number to the 1/3, where this x position is defined so that it is the the trailing edge of the plate, or it's just it could actually be a position shorter than that, but it's the region for which you want to find an average heat transfer coefficient that starts at x equals 0 and ends at a position such that it encompasses all of the laminar region into the turbulent region. So this expression, if I want to find the heat flux average over the entire plate, requires that I find the convection coefficient that is the average over the entire plate. So the entire plate length is L, or 0.5 meters, and we've already calculated the Reynolds number at that position. So here then the Nusselt number would be equal to 0.037 times this Reynolds number of 1.08413 times 10 to the 6 raised to the 4/5 minus 871 times the Prandtl number of 0.7111 raised to the 1/3 power. So that now we can calculate the Nusselt number, .7111 raised to the 1/3. All right, so I get here 1,445.42 as the Nusselt number at the, well, this is the Nusselt number for the plate that would allow us to calculate the average heat transfer coefficient. So this heat transfer coefficient then is, excuse me, is the expression of expression for consideration of a laminar and a turbulent region. So this is set equal then to the average heat transfer coefficient that will be over the entire plate times that length divided by the thermal conductivity, so that the average heat transfer coefficient then is K over L times the Nusselt number. So the thermal conductivity is 0.03095. The length of the plate is 0.5 meters, and the Nusselt number is 1,445.42. All right, so I get an average heat transfer coefficient that is 89.47 watts per meter squared Kelvin as the average heat transfer coefficient over the entire plate. So that says that the heat flux, that is the average over the entire plate, is 89.47 times the temperature difference. The surface temperature is 180 degrees minus 20 degrees. So this average heat flux is 14,315.4 watts per square meter for the heat flux. Now we want to compare that to the heat flux that we get just out of the laminar region. Again, where that laminar region is only from 0 to 0.2306 meters. So to find the average heat transfer coefficient, Q dot average for the laminar section, well, we know what the position is at which the laminar section ends, so we can calculate the Reynolds number at the transition point, and we know that the Reynolds number at the transition point is 500,000. That's the way that we found this expression of where the transition point ends. So this is from 0 to 0.2306 meters. So the average Nusselt number for the laminar region is 0.664 times the Reynolds number raised to the 1/2 times the Prandtl number raised to the 1/3. So for the laminar section, which is again from 0 to 0.2306 meters, and is for Reynolds numbers from 0 to 500,000, this expression then is 0.664 times the Reynolds number of 5 times 10 to the 5th raised to the 1/2 times the Prandtl number of 0.7111 raised to the 1/3 power. So that this Nusselt number that will give us the average heat transfer coefficient just for the laminar region, here is 0.664 times right. So the average, or this Nusselt number, is 406.457. And so the average heat transfer coefficient is just the thermal conductivity over that X position. That X position is the critical position here, times the Nusselt number. So the thermal conductivity of the fluid is still the same value, 0.03095. Now this position is 0.2306 meters times a Nusselt number that is 406.457. So the average heat transfer coefficient times 0.03095 divided by 0.2 is 54.5526. So if I wanted to draw this on H as a function of X here, if I indicate L and X sub CR here, the average heat transfer coefficient in the laminar region is 54.55. The average heat transfer coefficient over the entire plate is 89.47. So what that says, how do I get an average value for the heat transfer coefficient that is higher over the entire plate compared to over the laminar? It just means that I have, when there's a transition from the laminar flow condition to the turbulent flow condition, I just get a much higher heat transfer, average heat transfer coefficient for the turbulent region. So this might, if I wanted to draw H as a function of X, no, I just want to use a different color here. In the laminar region, the average heat transfer coefficient will be twice that at that which exists at the end of the laminar region. So here, this would be about 27.27 watts per meter squared Kelvin. And there'll just be a variation that looks like this. And then for the turbulent region, it will look something like this. So that I get an average value for the laminar region and an average value for the heat transfer coefficient over the entire length of the plate that includes a laminar and a turbulent region here. So when we consider these functional dependencies for the heat transfer coefficients, the that dependence is on X, but the properties and the fluid velocity have a major role to play because those are part of the calculation of the Reynolds number. So if I go back, well, here, let's see, I think I had a Reynolds number. Well, we calculated it first here. The velocity and the kinematic viscosity are going to affect the calculated value of the Reynolds number. And of course, the Prandtl number and the thermal conductivity, which are directly fluid properties, are also going to be used for the calculations of the quantities that we're looking for to actually solve these problems. So determining whether it's going to be laminar or turbulent is going to be dependent on the properties. By using the average, would we be able to find the average heat transfer coefficient of the turbulent region using the average of the whole plate and of the you could do if you did a weighted average, you could say that if the average over the entire plate is the average of the laminar region times the length of the laminar region plus the average over the turbulent region times the length over the turbulent region will be equal to the average over the entire of the entire plate times the entire length. And you could back calculate it, or you could use the expression that is for the turbulent region. This will just give you the expression of the heat transfer coefficient from the transition point to that X position. All right, so let's look now. Now, external flow over a plate is one condition. But as I was at the beginning of lecture here, I said external flow applies to any object that would be in a flow field where far enough away from the object, the free stream velocity and the free stream temperature would still exist. So for those problems, the two that we primarily pay attention to are cylinders and spheres. And they have different correlations associated with them because there's no differentiation for cylinders and spheres of well, we do define a laminar and a turbulent flow condition, but the correlations that we reference apply to both the laminar and the turbulent flow conditions. There aren't separate correlations for each of them. Now, when we're considering a cylinder and a sphere, when we're considering how fluid moves over these surfaces, now I'm going to draw here. The first one, just a cylinder. Now we consider that in a flow where we have a free stream velocity and a free stream temperature. If you recall from the fluid systems where we're going through hydrodynamics, we'd have streamlines that could be drawn over, and I'll just draw them over the top here, that will move over the body here. Here, this a cylinder. So the way that the fluid interacts on the front side or the upstream side of the cylinder is different than the way that the fluid interacts on the downstream side of the cylinder. And if the hydrodynamics are different on the front compared to the back, then the heat transfer is going to be different from front to back on a cylinder. And if you notice as you were reading, there were some expressions of Nusselt numbers as a function of angle, so that there's an angle theta that is from 0, and they don't go quite to 180. I think they typically goes to about 160 degrees from 0 to about 160 degrees, there's a variation of the Nusselt number as a function of theta. And if the Nusselt number is defined in terms of the heat transfer coefficient, that means the heat transfer coefficient varies as we move around this cylinder. That just says that the local heat fluxes around the cylinder are going to be different. But the reason that single correlations for cylinders and spheres are presented is because, unlike in a flow over a flat plate, where the length of the plate is going to determine what kind of heat flux variation you get and that you're interested in, well, when we're considering cylinders and spheres, we're often interested only in what is the heat transfer rate out of the entire perimeter. So even if the heat transfer coefficient is varying over the entire surface, the average value of the heat transfer coefficient is all that we need for the entire surface. We're typically not looking for what is the average heat transfer coefficient from 0 to 90 degrees. And that's because usually heat transfer from a cylinder is due to it being maybe a pipe or a tube in a cross flow of air or water or some other fluid, such that cooling or heating of that surface is occurring over the entire surface. And so we just want an average value with knowledge that there is a variation in the heat transfer coefficient over the entire surface. But if we can get just what is the average, then that will actually suffice. So when we're considering heat transfer coefficients over cylinders and spheres, it is always for the calculation of an average value that exists over the entire surface so that we can then calculate a heat transfer rate. Did we solve for Q average for the laminar section already? Let's see here. No, I didn't, but it's Q average for the laminar is H average times the same temperature difference. So the temperature difference is 160 degrees. So 160 times this quantity will give us that expression. Let's see. Go ahead. So this is 8,728.42 watts per meter squared. And of course, there would be a lower heat flux because the heat transfer coefficient is lower in that region compared to the entire plate. So when we consider the expressions, there are two now, and so for in a cylinder, the fluid moves just around the perimeter of the cylinder, but in a sphere, it moves. There's now instead of there just being a radius that is that we could consider just to be in the flow direction, because of in a cylinder, the length or the axis of the cylinder would move into and out of the page here, whereas in a sphere, the fluid moves around that circular radius in all three dimensions. So we have different correlations for cylinders and spheres, but both of them are used to find average heat transfer coefficients that exist over the entire surface of the object. Now, for a cylinder, the expression is that the Nusselt number is defined as H times D over K. Recall that the first time that I defined the the Nusselt number, it is the heat transfer coefficient times the characteristic length divided by the thermal conductivity of the fluid. Well, for cylinders and spheres, the characteristic length that is used is just the diameter. There's no X position that varies, and that's because in the cylinders and spheres, we're only interested in the average values over the entire surface. So when we're defining these Nusselt numbers, the Nusselt number is defined in terms of the diameter of the cylinder or the diameter of the sphere. So with this definition for the cylinder, the Nusselt number will be defined as 0.3 plus 0.62 times the Reynolds number raised to the 1/2 times the Prandtl number raised to the 1/3 divided by 1 plus 0.4 divided by the Prandtl number raised to the 2/3. This entire quantity in the denominator raised to the 1/4 times 1 plus the Reynolds number divided by 282,000. And that quantity, oops, two of them here. This one raised to the 5/8. And in the brackets, this is all raised to the 4/5. Now, this expression for the Nusselt number is much more complex because, again, this has to take into account what would be considered laminar and turbulent flow conditions. During laminar flow conditions around for a cylinder, these streamlines are would basically there's no flow separation that would occur, in that the streamlines would be not only mirror images on the top and bottom, but also front to back for extremely low Reynolds number flows. When we get to high Reynolds number flows, these streamlines look something like this. And there would be a region around the backside where there will be flow reversal, and you'll actually get fluid to, instead of just continue moving from left to right, you'll get this rotation in the flow. That is for what we consider turbulent flow conditions, and you basically end up with a much larger pressure drop from the front to back of the cylinder, but you get much higher heat transfer coefficients on the backside due to the rotation of the fluid that increases the interaction of the fluid molecules with the solid surface. So we have one expression that is to embody both laminar and turbulent flow conditions in one expression for this cylinder. But still, you're going to use the Reynolds number. Now, the Reynolds number is just going to be defined as the free stream velocity times the diameter divided by the kinematic viscosity. So that length that's in the numerator is just the diameter. So in order to calculate, let's say, eventually the heat transfer coefficient, of course, I'm going to need the thermal conductivity, the Prandtl number, and the Reynolds number. Just as we did before, the Nusselt number had in this definition the Reynolds number and Prandtl number. There's just a different functional dependencies for each of them. And to move from the heat transfer, or move from the Nusselt number to the heat transfer coefficient, we need the thermal conductivity, where the viscosity of the fluid is indicated in the Reynolds number itself. For this correlation, when we're calculating the Nusselt number, from here, again, the heat transfer coefficient now just becomes K over D times the Nusselt number, where the Nusselt number is just defined by this expression. That will give you the average heat transfer coefficient, so that the heat flux is just going to be this heat transfer coefficient times the temperature difference between the surface and the free stream temperature of the fluid. Now, for all of these properties, the kinematic viscosity, the Prandtl number, and the thermal conductivity, here we evaluate all the properties at the film temperature, which is just the surface temperature plus the ambient or the free stream temperature divided by 2. Now, here, so when we're calculating quantities for the cylinder, it's not much, it's not a whole lot different than for flow over flat plate, except that there's no transition to consider at all when using this correlation for a cylinder. For a sphere, we have a different correlation because the dynamics of the fluid flow Again, it can move not only over the top and bottom of the sphere, but around the sides of the sphere. So the Nusselt number correlation looks different. The Nusselt number is still going to be defined as H times D over K, but the correlation that defines the Nusselt number is different. It's 2 plus 0.4 times the Reynolds number raised to the 1/2 plus 0.06 times the Reynolds number raised to the 2/3 times the Prandtl number raised to the 0.4 times a ratio of the dynamic viscosity evaluated at the free stream temperature divided by the dynamic viscosity evaluated at the surface temperature raised to the 1/4 power. Now, know that these correlations are defined, they're defining dimensionless parameters and defined in terms of dimensionless parameters. These expressions are basically fits to empirically derived data. So someone did experiments with multiple different fluids with different sizes for different temperature ranges, and they did a fit of the data. And these expressions for both the cylinder and the sphere are best fits of the data sets that were collected. So these functional dependencies, particularly for the Nusselt number, where here you see the Reynolds number to the 1/2, Reynolds to the 2/3, raised to the Prandtl number. Well, in this expression, you have something kind of similar. You have the Reynolds number times the Prandtl number. Here you have the Reynolds number. You also have the Prandtl number in the denominator here, which you could, so here, when you're considering how the Reynolds number and Prandtl number are used, they just look different in the development of the correlations that were fits to the empirical data that were expressed now, or that were collected. Now, when using this expression, the film temperature is not used at all. Here, all properties are evaluated at T infinity, the free stream temperature, except mu sub s, where this is evaluated, which is evaluated at the surface temperature. So when evaluating, let's hear the Reynolds number again, will be defined the same way for the sphere as it is for the cylinder. The Reynolds number is the free stream velocity times the diameter divided by the kinematic viscosity. So when you're looking up the kinematic viscosity, the dynamic viscosity, and the Prandtl number, and also here the thermal conductivity, all of those evaluated at the free stream temperature. And then the dynamic viscosity, so you get this from the same table, but you, instead of evaluating it at whatever the free stream temperature is, you just evaluate it at the surface temperature. So those two correlations are the ones that we typically are going to use for the cylinder and for the sphere. Now, well, actually, this is the only one that is presented for the sphere. Now, there are some other expressions that we can use for a cylinder that are included in table 7-1. In table 7-1 are the results, or are multiple empirical correlations for the average Nusselt number for external flow over circular and non-circular cylinders in a cross flow. So here, this cylinder that I drew, when the fluid is moving over the perimeter, that's called a cylinder in a cross flow. But if you want to consider, let's say, a cylinder in a cross flow, or a square in the cross flow, or a diamond shape in a cross flow, or an ellipsoid or not, an ellipse in a cross flow, you would use table 7-1. And in table 7-1 is a range of Reynolds numbers and Nusselt number correlations. So there are Nusselt number correlations in table 7-1 for multiple shapes in a cross flow for ranges of Reynolds numbers. So these expressions, now typically, if you're dealing with a cylinder in a cross flow, this expression for the Nusselt number is the one that you would use. But this only applies to a cylinder, and this equation or this correlation only applies to a sphere. If you're considering, let's say, this might be a square pipe or a square duct that has air flowing over it, and you want to find the heat transfer coefficient on the outside. Or if it's a diamond shape, so it could just be a square where instead of the fluid moving in all of these, the fluid is moving from left to right. So here, essentially this diamond is just a square that is rotated 45 degrees, so that the way that the fluid interacts with this exactly the same shape is different because of the way the fluid would move over the surfaces and give you different average heat transfer coefficients over the entire surface. But you use those correlations from table 7-1 so that once you've calculated the Reynolds number, which would tell you what range of Reynolds number that you have acting on your particular shape, and then you would select the Nusselt number correlation that goes along with that range of the Reynolds number, and you could calculate for these irregular shapes in a cross flow. But you could also do it for this cylinder rather than use this expression of a correlation. Now you will get slightly different answers, and that's why you just have to reference which correlation you're actually using when making a calculation for that particular problem. So these, when working with the correlations that we're going to be, that you're already exposed to in chapter 7, that you'll see in chapter 8, it's important that you, important that you identify what type of flow is it. Is it external flow over a plate? Is it external flow over a cylinder or a sphere or some other shape? Then, okay, but once you determine that, well, what is the Reynolds number? So that the Reynolds number will guide me to the appropriate correlation. And then how do I get the properties? For the flow over flat plate, all of those evaluated, the properties are all evaluated at the film temperature. For this cylinder correlation that I presented, this is at the film temperature, or the properties evaluated at the film temperature. For the sphere, it's the free stream temperature and the surface temperature. And in table 7-1, all of those properties evaluated at the film temperature. So here, we'll just write that as a note. Properties evaluated at TF, the film temperature. So when we're working these kinds of problems, identifying all of the conditions that guide you to the appropriate correlation is all that we're doing. And again, in the previous problems, before we got to chapter 6, heat transfer coefficients were just specified, and we use them. In these chapters, 7, 8, 10, the heat transfer coefficient is calculated based on what we know about the flow conditions, what we know about the temperatures and the fluid that is actually being used to provide the convection for either heating or cooling off the surface. So let's look here for a cylinder problem. Can at least get it set up. in these last 3 minutes here. We consider a cylinder in a cross flow. And we can actually look at how we could solve this by, we have this cylinder correlation, and we'll also look at the appropriate correlation for a cylinder in a cross flow from table 7-1. But here we'll consider that there's a diameter associated with the cylinder in a cross flow, so that there's a free stream velocity and temperature that exists for the fluid with a surface temperature. Here we'll consider that the diameter is 12 centimeters and the surface temperature is 90 degrees C. And the fluid that's flowing over, this is air, at a temperature that is 7 degrees C. And the free stream velocity is 65 kilometers per hour. And we want to determine, well, what is the heat flux on the surface? So here's a cylinder in a cross flow. Now here, again, we don't have to determine whether it's a laminar or turbulent. We just need to get the Reynolds number because we'll use that. The Reynolds number here is the free stream velocity times the diameter divided by the kinematic viscosity. In order to get the kinematic viscosity, we have to find the film temperature, which is just Ts plus T infinity divided by 2. And actually, let me change this air temperature so I don't have to do any interpolation here. Let's just say air at 10 degrees. So here is to be 90 plus 10 over 2. So this 50 degrees is the temperature at which we would evaluate all of the properties for the air so that we can go to the table for air. And this is atmospheric air, just to make it very specific so we're in the right tables. So this is table A, I think that was 15. Yeah, table A15. So for 50 degrees, the thermal conductivity, the kinematic viscosity, and the Prandtl number. So we can use those quantities, 0.02735, .07235, 1.798 times 10 to the minus 5 meters squared per second, watts per meter Kelvin. This is for the kinematic viscosity, and the Prandtl number, 0.7228. So those are all the quantities that we'll need in order to use this, calculate the Reynolds number, and then use the Prandtl number and the Reynolds number along with the thermal conductivity to eventually get the values of the heat transfer coefficient. So we'll next time we will start with calculation of the heat transfer coefficient using this expression. And we'll also reference table 7-1 and get the appropriate expression of for the calculation of the Nusselt number and thus the heat transfer coefficient using those tables, and compare the values of the heat transfer coefficients that we get using those two different methods. Again, neither one is right or wrong. They're just different correlations. They're developed with different sets of empirical data. And so you get different results. And again, it's just important that you specify what correlation was used in order to make the calculation. All right, well, that's it for today. Hope you enjoy the rest of your day, and I will see you on Monday. And we'll